Bridges, arteries for a nation's commercial lifeblood, evolving through the ages, from small to large, simple to complex, always the very expression of the engineer's art. Bridges, a major area of concern for many municipal officials, but a partial answer to that concern now appears. An answer for the future, drawn from the experience of the past. Modern timber bridges. Timber bridges to the man in the street. Timber bridges, a step backward to some highway bridge engineers. But modern timber bridges are practical, are safe, and can be very economical. Modern timber bridges that could be the answer for the municipal manager with large bridge needs and a small budget. That concern and others were addressed at a national conference held at University Park, Pennsylvania in May 1987. We will look at modern timber bridges from the overall aspects of design, fabrication, installation. And while we're doing that, have an opportunity to address other items such as the transportation of bridge components, the maintenance of completed bridges, and the economics of modern timber bridge design. And additionally, provide some common sense tips and hints for all types of modern timber bridges, while focusing on the stressed timber type, which was the type put in as part of the bridge conference. Let's start at the beginning. Bridge design. Modern timber bridges are designed, as are all bridges, with safety, reliability, and long life as the designer's guideposts. Nearly one-half of the bridges in the United States are listed as either structurally deficient or functionally obsolete, with about 75% of them on secondary or rural roads. New ideas for designing and building bridges have become an immediate concern. This concern translated into renewed interest in timber bridge design.
Our research has centered around taking work that has already been done in Canada and research work we've been doing in our laboratory and trying to develop a design guide for stress laminated decks that could be incorporated into the AASHTO specifications.
Our research and implementation in Ontario, coupled with the accelerating R&D and implementation in the United States, will soon make the use of our North American technology in wood bridges recognized around the world.
Another area where timber bridges can play a bigger role is that of alternate designs. We at the federal government encourage competition between different materials, different construction techniques where it can be used. Timber certainly can play a bigger role than it plays right now. We know that we've had some great competition between steel and concrete at particular bridge locations where they've both been suited. And we think that timber, particularly for local governments on local roads, may play a much larger role in competing one-on-one against alternate materials.
Detailed information on timber bridge design is available from a variety of sources, both public and private. Timber bridges have evolved from the simplistic to the historic to the functional, as in these nailed decks, to the modern, as in the glue-laminated approach. If the thought of gluing together a bridge seems strange, listen to what NASA thinks about using glue.
Scientists at NASA Langley Research Center are developing and testing special composite lightweight materials that are used in building spacecraft. The composite material is made of graphite filaments impregnated with an epoxy resin. Aircraft made with composite lightweight structures save fuel.
NASA's experiments centered around artificially duplicating what is the natural adhesive in wood, lignocellulose. Further refinements of modern timber bridge design have evolved to the stressed timber bridge, the type of bridge that was installed as a part of the Timber Bridge Conference. We have looked at general concepts and uses for timber bridges, as well as talked about the design of timber bridges. The key to success begins with the treatment of the timber itself. So let's start there. The arrival of the raw wood. While many types of timber have been used for bridge construction, this firm, Wheeler Consolidated, St. Louis Park, Minnesota, prefers Western Douglas fir. The timbers are unloaded and the treatment process begins. First, the wood is incised to give a pathway for the treatment material. Then trimming begins to occur. Notice that all of this work is done prior to the treatment of the wood. The wood is well formed, and all machining is completed before the actual treatment process. Machining to include incising, to include the preservative penetration, as well as the operation of cutting, framing, or drilling of the holes. The wood is then loaded on a tramway capable of carrying 3,400 board feet and taken into the treatment cylinder. While it's in the cylinder, the technician uses the control panel to check the treatment procedure. The wood is taken out of the cylinder. In good treatment plant operations, easily treated wood and resistant woods are not included in the same package. The easily treated wood, under such conditions, would absorb more than the average, and the resistant material would absorb less, so the types of wood are not mixed. Test borings are done to measure the treatment penetration. Actually, much of the testing and review of the treatment procedure is done in the lab. Now the treated wood is prepared for assembly. Shipping rods are threaded through the pieces, pre-drilled and pre-formed. The rods are tightened and stressed. This stressing procedure is much the same as you will see in the actual erection of this post-stressed bridge. The stressing is sufficient to keep the bridge from separating. The loaded deck is then shipped to the bridge site. Even as the timber bridge was being fabricated, work was going on at the construction site. The timber bridge was to replace a concrete pier bridge that was too narrow for the proposed development plans in the area. The roadway was closed and the preliminary work was begun. And the old bridge was ready for removal.
Oh, right there. Let me get a couple more. Come on, go out for another one. You gonna get? Couple more. Bring the heart.
Here, a major change was encountered. The original abutments were viewed as too worn and too poor to be kept, so a decision was made to place new concrete abutments. Piling was placed to divert the stream flow. Forms were constructed, and the new abutments were put in place. Timber bridges are usually installed on rural roads, and this may limit your choice of where you can position the crane. The site was now ready for the arrival of the bridge components. Another item of consideration is the unloading procedure itself. Remember, you are dealing with fabricated and treated wood material. But here is the expert.
There's an old saying that beauty is skin deep, and in some respects this applies to treated timber also. The protection is only skin deep. And if we blemish or bother or damage that, we're going to seriously impair the long-term durability of the timber. We can take excellent timber, we can fabricate it very carefully, we can treat it according to specifications. And yet all of that can be negated in just one careless moment through improper handling or transportation. So today we want to look at a couple of things that are essential in the transportation and handling of treated timber.
The unloading is done in a predetermined order. All the hardware for the bridge, pins, bolts, and the tensioning rods are unloaded first. Next, the prefabricated rails and pier caps. Note the wooden blocks used to prevent the chains from damaging the wood. The pier caps are set a measured distance apart. The pier caps will be used to provide support for the bridge deck panels. In effect, they are creating a field workbench. Throughout this installation process, you will see an almost complete absence of sophisticated equipment, unless you count the crane as sophisticated. The crane, a hydraulic jack, are all that is needed except for the ordinary hand tools found in any municipal garage. Pipe wrenches, sledges, crowbars, etc. This bridge will be built with those tools and township employees. That's one of the major benefits of modern timber bridges. Regardless of type, nail deck, glue, laminated, or pre-stressed, you need only the minimum of equipment and your own personnel. There are 4 prefabricated panels, A and B, C and D. And here are the plans that show that. The plans may seem simplistic, and they are. Remember, one of the keys to modern timber bridge installation is that it can be accomplished by a semi-skilled workforce under the direction of your resident engineer or an experienced bridge construction supervisor. The 4 panels were assembled at the plant and shipped with 8-foot thread bars tensioned to keep the various pieces together. At the construction site, the panels are placed in pairs, panels A and B, C and D. The tension is released from the shipping thread bars, and the 8-foot bars are removed and replaced with bars 14 or 15 feet in length. Then they in turn are tensioned. Panels A and B are then combined to form one large panel, actually 1/2 of the bridge deck. The procedure is repeated for panels C and D. We now have 2 half decks. Bridge pier caps are installed on the concrete abutments. The bridge site is now ready for the placement of the bridge deck. The first half deck has been installed. When the half deck is being lifted, the crane is lifting 20 tons and reaching out a considerable distance. So the crane must have a sufficient lifting capacity. The second part of the deck is positioned on the pier caps, an activity that combines machinery and muscle. The 2 decks are now seated, but not joined. It is this joining process and the tensioning that makes this bridge type unique. The eye bolts used to secure the cable are removed. The decks are further aligned using this rod alignment tool. the locking nuts from the interior side of the half deck are removed. The rods are turned out to a sufficient distance for joining. This length is assured by the simple step of painting the ends of the rods with red paint. The rods are tensioned to a pressure equal to 90 to 100,000 pounds per square inch. The decks are pulled together by this tensioning. The guide rails are assembled and installed. A bituminous wearing course is applied and the bridge is completed. The timber bridge was completed after 5 days of actual field construction. Since this bridge is the focal point not only of the conference but of a great deal of interest by federal, state, and municipal officials, a research program was begun to evaluate the tensioning technique used in the construction of this bridge. The purpose of this research effort is to determine the forces in the transverse post-tensioning rods over a period of time. The action force will be measured with load cells which have been placed on 3 of the steel bars. The 3 bars selected were located near the support, quarter point, and mid-span of the bridge. It is felt that the forces in these bars are representative of the forces of all the transverse bars in the bridge. Measurements will also be taken for moisture content and camber or the deflection of the bridge. Moisture content directly affects the force in the bars because of the shrinkage and swelling. The tests are being taken on a weekly basis, and a research report will be issued by the Pennsylvania Department of Transportation. No discussion of bridges would be complete without a mention of maintenance. For the older types of timber bridges, much of the maintenance concern focused on controlling decay caused by wood-boring insects, marine organisms, and living fungi. However, for modern timber bridges, the focus has shifted. First of all, preserved wood must be regarded as an entirely new structural material and not just an improved form of wood. So our maintenance concern is now, as with any type of bridge, on preventing trapped moisture from occurring. Remember, when you do your maintenance inspections on modern timber bridges, you're also checking to be sure the protective envelope has not been marred. In short, good modern timber bridge maintenance is good bridge maintenance. Wood is a marvelously adaptable structural building material. When it is treated with a compatible preservative, as we saw in the earlier sequence on fabrication, it will not suffer early decay. It is economical, practical, and long-lasting for many short-span bridges, that is, in the range of 15 to 60 feet. It is simple to fabricate, is lightweight, and is easy to install, has a high strength-to-weight ratio, has excellent sound and thermal insulation properties, has good shock resistance, has surprisingly good fire resistance. When large structural timbers are exposed to fire, there is delay as it chars and eventually flames. This slow rate of fire penetration means that the bridge's structural members subjected to fire maintain a high percentage of their original strength. It is immune to de-icing chemicals, has unique aesthetic qualities, and is a renewable resource. What can you get? One of the most common modern timber bridges is the glue-laminated or glue-lam bridge. Glue-lam consists of 2 or more layers of wood glued together with the grain of all layers, or laminations, approximately parallel. Glue-lam bridges are very adaptable to a variety of bridge sites, and because the bridge panels can be fabricated and easily erected on-site, they save money. The pre-stressed bridge, featured in this program, appears to have its greatest future for medium-span bridges. Who to talk to? You might begin with the sponsors of the Timber Bridge Conference. An excellent source of information is your local RTAP engineer. RTAP, Rural Technical Assistance Program, dedicated to the transfer of technology. Timber bridges have already been constructed in Pennsylvania and other states at significantly lower cost than bridges made of traditional materials such as concrete and steel. Even more significant savings have been realized when fabricated bridge decks are placed on existing or new timber abutments, savings of 25 to 40% below conventional construction costs are common. The purpose of this program is to provide information to local decision makers and those who may be involved in the manufacture of timber bridges. Modern timber bridges, a viable alternative.